Hello everyone. In this lesson we're going to take a look at factoring, and we're going to look at factoring with different scenarios that you might be used to seeing. And I'm actually going to start with one that might be new. This is called factoring by grouping, and the first thing I want you to notice is that these are four-term polynomials. And usually when we've factored in the past, we've either had a binomial or a trinomial. So this right away looks different from what we've seen before. And the idea behind factoring by grouping is that you want to be able to take a look at groups of things and see if they are factorable. So we're going to look at 1a here. So in 1a, we have ax plus bx plus ay plus by. And you can see that the first two terms share an x in common, and the second two terms share a y in common. And there's a common, I shouldn't say common, but there's a similar coefficient of a for the first two and a similar coefficient of b for the first two. Now, usually it's the x's and y's that control what is grouping together, because like terms are defined by those variables. A and b would be representing coefficients, which actually be numbers. Okay, so just to talk about that quickly. So I can therefore factor an x out of these first two terms. If I just consider these two terms, both of them have an x in common, so I can pull that x out as a common factor. And that leaves a plus b behind. And over here, I can do the same thing with the y. I can pull a y out of both as a common factor, and that leaves an a plus b behind. Now, this gets a little bit confusing for students, specifically because it's written so that the x is the first variable and then the coefficient is second. So usually, we would write this like this, and I'm going to do that because I want to make a point here. I'm going to put the a plus b's in front of the actual two variables. So what we have here is a scenario where we have another common factor. A plus b is a factor because it's multiplying x and multiplying y. And I'm just going to highlight that with a dot between the two. Anything that multiplies is a factor. Well, because a plus b is the same here and the same here, it's a common factor. That means I can take that common factor and pull it out in front. But it is a little bit difficult to see that that is a common factor. So I just want you to compare that for a second. Let's say we had 2x plus 2y. Now you can clearly see that the 2 is common to both terms, and therefore I can pull the 2 out in front, and I'd have x plus y left over. Well, I can do the exact same thing with a plus b. Now, some people think that it's a little bit difficult to see, and you can do something called a variable substitution if you want to help yourself see what's going on here. And usually with a variable substitution, you're going to use like another letter. We usually use a capital letter to do this. So let's set capital X to equal a plus b. Just temporarily. Now you don't have to do this, but it might help you see what's happening. So a plus b is now going to be replaced with capital X. Can you now see that that capital X is in the same position as the 2's were here in the example off to the side? So we can factor out that capital X. And we're going to have x plus y left over. And if you use a variable substitution like this, at the very end, you're going to resubstitute what the capital X was. We had set capital X to be a plus b. So we're going to resubstitute a plus b in there. And now you can see that the a plus b from the line above right here has been factored out in front of the x plus y, which has been grouped together in a second bracket, and we have now factored this by grouping. So this is optional. You don't have to do the variable substitution. But sometimes it does help, and we will be using it later on in certain situations as well. So we can look at another example here. I'm just going to add a page here. So let's take a look at something like D. Okay, so I'm going to have to try to remember that. So it's x squared y minus y squared minus x cubed plus xy. I'm just going to go make sure that I got that right. I do. Now, one of the things you've got to be careful with is sometimes they won't be grouped in the right grouping order. You might have to rearrange things and look a little bit deeper into the equation. But you are trying to group them so that when you factor something out, you get the exact same thing in both groupings, okay? Now, so for instance, here I can see that I can factor out a y from both of these terms, okay? Can I factor out a y from both of these terms? No, but I can factor out an x from both of these terms. If I factor out a y over here, can you kind of see what you're going to have left? You're going to have an x squared left, and you're going to have a y left, right? There's going to be a subtraction between the two. Over here, if I factor out an x, I'm going to have an x squared and a y. Well, I have an x squared and a y here, so that looks like the right grouping. However, there is a subtraction between the two terms here, and there's an addition between the two terms here. So that's going to require us to have a sign change. Well, there is a negative in front of this x cubed. So instead of factoring out an x, we're going to factor out a negative x. So let me show you what that's going to look like. So we're going to factor out a y from these two terms. Common factoring. Now I'm going to factor out a negative x from the next two terms. So factoring out a negative x from negative x cubed gives me a positive x squared, and now that term matches with this one. And factoring out a negative x from positive xy is going to give me a negative y, and now this term matches that one. So I have successfully factored by grouping because these two brackets are not going to be the same. And just like we did in the previous slide, now this time I'm going to skip the variable substitution. I'm trying to get you to eventually be able to not have to do that for factoring. You can see that this x squared minus y is common to both of those terms. So we're going to pull the x squared minus y out in front. What's the leftover in both positions? Well, the first leftover would be y here, and the second leftover would be negative x here. And that is another example of factoring by grouping. So if you had done a variable substitution and called this capital X and called this capital X, you would have factored out the capital X out in front, right? So you can do that if it helps you visualize what's happening, but you should now start to be able to see that these two brackets are the same in both terms, therefore we can factor it out in front. Now, I'd like to look at another scenario with factoring, and this time we're going back to trinomials. And I have an example down here, but I'd like you to ignore that example for just a second. One thing you may or may not have seen is trinomials with two variables. So I just want to foil something to show you how it works. So let's say we had, instead of x plus 3, let's say we had x plus 3y times x minus 2y. Okay? And this is just a random binomial time binomial scenario. Okay? But I put two different letters. Usually you wouldn't have the second letter in the bracket. I just want to show you what happens when you actually expand this. So you're going to have x times x. X times minus 2y is going to give us minus 2xy. And usually we write the variables in alphabetical order. And then we're going to have 3y times x, which is going to give me plus 3xy. It is a positive because both of those terms are positive. And then we're going to have negative 6y squared. So there's a couple of things that are different here. Our two middle terms now have two variables in them. Now they are still like terms, so they still will group together. So that's one of the things that's different, but there is a similarity. And the last term now has a y squared attached to it, which we're not used to seeing with trinomials. Normally the last term in a trinomial is just a number. But now we just have that y squared because it came from the two terms that contained y's in the last terms multiplying each other. So we're going to have x squared plus 1xy minus 6y squared is our answer. And there's our trinomial with two variables in it. So what we want to do is we want to work backwards. What if I give you a trinomial that has two letters in it? Could you now go back and find the previous trinomial that it came from? So the first thing we'd want to do is check to see if there's any way that we can common factor a number here. And 25 has a factor of 5. Yeah, it might not be possible to common factor here. So because we can't find a common factor, if we started doing our product and sum calculation to see, 30, because this is a type 2 trinomial, normally we would do 36 times 25. Already that's going to be a really, really big number, right? So one thing you might want to check to see before you do anything else is this a perfect square trinomial? So a perfect square trinomial has an interesting pattern to it. If you square root the 36, it gives you 6. And if you square root the 25, it gives you 5. Then you would check to see if you multiply the 6 times the 5 times 2, do you get the middle number? And here the answer is yes. 6 times 5 is 30. 30 times 2 is 60. Now 60 is negative, okay? So we'll talk about that in a second, but this is actually a perfect square trinomial. So in a perfect square trinomial, the result is usually two brackets that are exactly the same. And we'll talk about how we're going to simplify that in a second. But inside the two brackets, what you're going to have is the square root of the 36 plus the letter s, okay? And then you're going to have a plus or a minus the square root of the last term, which would be 5, and the t. And the sign here tells you whether or not it's going to be a plus or a minus between the two. So it is going to be a minus in this case because it is a subtraction between the two. So that is a perfect square trinomial, which we can then write as 6s minus 5t all squared. And if you foiled that, 6s times 6s is 36s squared. And then you'd have a 6s times a minus 5t, and then another 6s times a minus 5t. And there's where the 6s minus 5t comes from, which gives you that double of the 6 times 5, okay? So that's a special case in two different ways. One of them being that it is a perfect square trinomial, and secondly, because it does have the two letters in it. Other than that, this technique is the exact same as factoring any kind of trinomial, whether it be type 1 or type 2. The main difference is, do you have two letters in it? And if you have two letters in the trinomial, you're going to end up with two letters within the brackets as well. So the next thing I'd like to look at are some differences of squares. We already know what a difference of squares looks like, but you can, same as with the trinomials above, you can have differences of squares that have two letters in it, like this, okay? So we know that the pattern for a difference of squares, very similar to a perfect square trinomial with one slight difference, is you square root the 64, you square root the c squared, and that's going to give you your first term, so that's going to be 8c, and then you square root the 25, and you square root the d squared, and that's going to give you your second term, which is 5d, and then you just put those in both the first and second positions of both brackets, but then one of the brackets is positive and one of the brackets is negative. Now, I should have suggested to check to see if there's a common factor before you start, but I quickly had looked at that and noticed that there wasn't one, but I'll just mention it now. Okay? So that's how you find the first and second terms of your brackets with the difference of squares. Now, looking at the example that I have here, does this also follow the pattern of a difference of squares? Well, we have the square of something minus the square of something else. So that is also a difference of squares. Now, the square root of a plus b squared is just a plus b, and the square root of c plus d squared is just c plus d. So when we write out our brackets, the answer to this is going to go here. So we're going to have a plus b plus the answer to this one, c plus d. And then in the second bracket, it's going to be a plus b minus, now in this case, we have to put a bracket here because it is a subtraction of the entire second bracket. So technically, you should have a bracket here as well, but you don't need that bracket because it is an addition. However, you absolutely do need the bracket here. And that means that you could then expand the minus into that bracket. I'm not going to do that, but it would become minus c and minus d. You can do that, but I just want to make sure it does look like a difference of squares still. So those are some interesting little twists to differences of squares. This might be new for all of you. This year we're going to learn about factoring a sum and difference of squares. There are two different formulas to know for this. Now, I am going to prove where these formulas come from at a later date, but for right now, I'd like you to start memorizing these two formulas. Now, there is a way to help you memorize it. So first of all, let's talk about the fact that there are two different formulas, one for the sum of cubes. So when you have two things that are cubed added together, you can expand it using this formula. So a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. For a difference, it's a subtraction between the two. So this is different from a difference of squares, which only has a difference of squares. This works for both a sum and a difference. Okay, so a cubed minus b cubed is equal to a minus b, and I want you to notice there's a difference right away here. And then a squared plus ab plus b squared, and there's a difference right away here as well. Okay, now there's an acronym that I discovered on the internet that helps students remember. If you look at the sign in the first bracket, it is the same as the sign in the original expression. Okay, so that's the same sign. And then if you look at the second sign, it is always the opposite. And then if you look at the third sign, it actually looks like it has a significance with the sign of the first sum expression, but it's a plus for the second one as well. So that last one is always positive. Well, if you take the first letter of all four of those words that I just highlighted here, you get the acronym SOAP. So same sign, opposite sign, and always positive. Now you have to remember that the AP of the always positive just represents one sign, but that does give you the acronym SOAP. Okay, so that might help you remember how to set this up. So let's look at some examples here. So what does a sum of cubes look like? So let's say we had x cubed plus 27. So both of these are cube rootable. Which is not a word, but I like to use it as a word. So both of them can be cube rooted. That's what tells us that it's a sum of cubes, along with the fact that it is an addition. So then you would use the sum of cubes formula. Now we need to know what our a is, and we need to know what our b is. Well, the a is just the cube root of x cubed, which is just x. And the b is the cube root of 27, which is 3. So now I'm just going to follow the formula for the sum of cubes. Now, trying to remember the SOAP acronym, it is the same sign between these two, and it is the a and the b. So we have x plus 3. And then you have to remember what it looks like. So I have the difference of cubes up here. It's very similar to this. You've got a squared, ab, and b squared. So a squared would be x squared, ab would be 3x, and b squared would be 9. And then this sign here has to be opposite the original one for the SOAP acronym. Same, opposite, and then always positive would be a plus there. And that's basically how a sum and difference of cubes work. Let's look at another example of that. So I could give you something like that. So our a value would be the cube root of x cubed again, which is just x. Our b value would be the cube root of 1 over 27, which is 1 over 3. Oh, and I forgot to cube root those, sorry. Okay, so the cube root of 1, the cube root of 27 is 1 over 3. So now I can fill in with my SOAP acronym again. So this is going to be the same sign. This is going to be the opposite sign. And this is going to be always positive. And then I just got to remember what goes in here. So this is always a and b. So a is x, b is 1/3. The number or the term over here is a squared. So that's x squared. The term in the middle is a and b multiplied together, which would be 1/3 x. And then over here, it's b squared, which would be 1 over 9. So once you can recognize a sum and difference of cubes, the rest should be relatively easy. There can be different combinations. I'm not going to show you every example, but you will have a chance to practice this at some point. So that'll be the end of that video. I hope you understood all of that, and if you didn't, please let me know with email or ask me in class. Have a great day.